In the previous fragment, I explained a strategy how to find an answer to the question whether every ideal is a kernel of the kernel of a homomorphism. And I outlined an implementation of this strategy. After all, we produced the quotient ring and we produced the homomorphism. Here is the description of the map. To check that the map is a homomorphism, I forgot to say that in the previous segment, is very simple. You can find details in the book, or just look how did we define the observations in this fraction, in this quotient ring. Quotient. How did we define the observation in the quotient ring? You look at the definition of operations on cosets. This is the set of cosets which we supplied with observations so that it became a ring. Now you look at the definition and see that the operations are defined in a way such that this is a homomorphism. So the to check that claim of the theorem is immediate. Details are in the book. If you've got confused, look what does the book tell you about that. I believe you can see that on your own that this is indeed true. The map is a surjective homomorphism. So our question is solved, and now a combination of theorems 6.10, which tells us that every kernel of a homomorphism, the kernel of a homomorphism is an ideal, the kernel of every homomorphism is an ideal, and this tells us that every ideal is the kernel of a homomorphism. So we can combine these two theorems into a proposition, a subset of a ring R is an ideal if and only if there is a ring S and a surjective homomorphism R to S such that K is the kernel of this homomorphism. We proved that the kernel of every homomorphism is an ideal, not necessarily surjective. But if we have a kernel of some homomorphism, it is surjective on the subring, which is the image of homomorphism. So we can always find a ring so that the homomorphism is surjective. If initial was not, with the same kernel, we take homomorphism to the image, which is a subring, and now it is definitely surjective. Another important question in this connection is the following: the question of uniqueness. We started with so let me formulate that. We started with a ring R and an ideal in R such that and we constructed a new ring the quotient ring R over I such that there is a homomorphism R2 with whose kernel is I. The question which we may want to address is whether this such a ring is unique. Is this ring unique? Well, first of all, this question is a little bit badly formulated. What does it mean, unique ring? Somebody else brings another ring, and after that we see that the two are isomorphic, but this is still a different one or the same one. So, specifically, or more precisely, are any two such rings, isomorphic. That is a meaningful formulation instead of this vague uniqueness. And the answer is no, not that fastly. A point is that I deliberately omitted the adjective surjective here. I just said a homomorphism. Then the situation may be as follows. The answer is no, because it may happen that we have R maps to R I, which sits inside a much bigger ring S. So no elements of R map here. This is irrelevant. But still, it may happen that the ring we found, whatever it is, sits inside a bigger ring. The kernel is still the same. The elements which map to 0 here are the same here. These elements are kind of redundant. No one element of R maps there. So in this, if we formulate the question in this way, then the answer is no, because there may be other elements in the ring S which are absolutely irrelevant but still are there, and R over I, the quotient ring, definitely is not the same as a bigger ring S. So a correct question would be with the word surjective. So we require additionally we require the homomorphism to be surjective. As the homomorphism from R to the quotient ring is. So this is a surjective homomorphism. So we ask whether the ring with such a property that there exists a surjective homomorphism with the given kernel is unique. Namely, are any two such rings isomorphic? And now the answer is yes. After that, and this is given by the first isomorphism theorem. Which is theorem 613 in the book, which tells us if F from R to S is a surjective homomorphism of rings with kernel K then the quotient ring R over K is isomorphic to S. So every S such that there is a surjective homomorphism with this kernel is the same. It is always isomorphic to the quotient ring. The proof of the theorem you will find in the book. I will give you an idea of this proof. To make it more transparent, and after that the proof in the book becomes quite clear and transparent. So we have two homomorphisms. We have a homomorphism from the ring R to the ring S, and we have a homomorphism from ring R to the ring R over I, to the quotient ring. An element A here maps to element F of A here. This is F, this is F. And maps to, by our construction, by this theorem, by theorem 612, this is pi, the homomorphism from R to the quotient ring. So this is pi, and the element A maps to the coset A plus I. This is the set of cosets. Now we define a map, or a map, which is called phi in the book, from the quotient ring to the ring S. So this is the arrow, which is going to be phi, the map from here to here. The definition is very, very simple. It is clear that, so we have no choice. We have element A here, the corresponding element coset here, and the corresponding element F of A here. So we map this one to that one to make it all consistent. So we map A plus I, a coset, to F of A. Now in order to conclude the proof, we want to claim that this map, so claim is phi is an isomorphism. So the two rings, the quotient ring R over I and the ring S are isomorphic, and we are done. What do we need to check in order to justify this claim? First of all, the map is defined using an arbitrary choice of a representative of the coset. If we choose another representative and land in a different element of S, then this map is simply not defined, because for what we have to define a map from the set of cosets. If, depending on which representative we are choosing, we end up with different elements in S, then this is not a map from cosets who is the image of coset of a given coset under phi. Which representative do we prefer? So the first order of business is to check that phi is well defined. That means does not depend. That means that who does not depend? F of A does not depend on the choice of the representative A of the coset A plus I. Of course, all representatives of the same coset differ by an element of our ideal I, and every element of our ideal I maps to 0. So the difference between two maps to 0. That is how do we check that. That is not the end of story, of course. After that, we gotta check that phi is bijective. That is surjective. Which is very easy. F was surjective, so every element of F is F of A for some A in R. Take the corresponding coset, it maps to F of A. The map is surjective and injective. Which is also not difficult at all. You're going to check that two distinct cosets do not map to the same element of S. Otherwise, the difference between the representatives is going to be in the kernel of F. That is what you check, and the kernel is exactly K. So, I wrote, sorry guys, I wrote I instead of K elsewhere. The ideal was denoted by K, and I wrote IL everywhere. That's a bad idea. So this is K, and this is K, and this is K, and this is K, and this is K. Oh, now it is consistent. So the map phi is bijective. It is surjective and injective. I explained briefly why. The details are in the book. And finally, phi is homomorphism. That is also easy. It comes from the fact that both f and pi are homomorphisms. So you consider a sum of two cosets, choose sum of representatives, take these elements, these representatives here, and map with f into the f is homomorphism, so sum of images is image of the sum. Not a difficult task at all. If my brief remarks are not very clear, you can look up in the book at details. This is the outline of the proof, which is given in the book quite clearly. And the question of uniqueness this way is also addressed. To sum up, ideals are always kernels of homomorphisms. Every ideal is a kernel of a homomorphism. For every ideal, we can construct another ring and a surjective homomorphism. For every homomorphism, even if it is not surjective, it is anyway surjective into a subring, which is also a ring, so it does not matter. For any homomorphism, its kernel is an ideal. Ideals, congruences modulo ideals, generalize in a very wide way the congruences modulo integers and congruences modulo polynomials, which we discussed in chapter 2 and chapter 5 correspondingly. In these chapters, it was also discussed that something interesting happens when an integer is a prime or the polynomial is irreducible. Both special cases turned out to be of special interest. In the next fragment, we will address these questions in general. What sort of properties of ideal correspond to the property of generator being a prime or irreducible? Thank you for listening.